Today we're going to be looking at section 2.2, which is the beginning of a two-day discussion about polynomial equations. So this is day one, and then it'll be day two. Yes, ma'am?
Sorry, I'm just trying to submit my...
All right, so polynomial equations. The first thing we're going to talk about is the zero principle of multiplication. Oddly enough, my 11th grade daughter was encountering this the other day as she tried to set two things multiplied together equal to 3, and I said that property doesn't work. It only works if it's equal to 0. So the property, the zero property says, if A times B is equal to 0, then it must mean that either A is 0 or B is 0. And that's very unique, right? It's not going to work for setting it equal to anything else. The one that my daughter was doing is she was trying to set it equal to 3 and then separate it out and make each part equal to 3. And I told her, like, that doesn't work, Abby. It doesn't work like that. So, but it works for zeros, and that's really friendly for us because it allows us to solve equations very effectively. So here's a couple of examples. I know that these don't look like A and B. They look like other things, right? I've got 5v plus 3, and I have 9 minus v. But when they multiply together, they give me 0, which means one of those two binomials that I just highlighted has to equal 0 for that to work. I can't multiply two things that aren't 0 and get 0. So one of those would have to be 0 to start with. So what you will remember doing is taking each part individually now and setting them equal to 0. At that point, it becomes a linear equation, which is what we were doing in previous sections of material, solving linear equations. We even did it back in Unit 1. So we will subtract 3 on the first one. So now I have 5v equals negative 3. And if I divide by 5, I'm going to move this one over here over. So if I take my pieces and I divide by 5, then v is equal to negative 3 over 5. So this is one of my solutions. If v is equal to negative 3 over 5, the yellow one that I highlighted will become 0, and it zeroes out the whole polynomial. Now it doesn't make the purple part 0, but it doesn't have to. So the purple part could potentially have a different solution as well. So we'll subtract our 9, or actually, you know what, we'll do it the other way. We'll add the v. And then we're done. So 9 is equal to v as my other solution. So again, if v is equal to 9, then the purple polynomial, that expression becomes 0, and it zeroes out the whole thing. The yellow part won't be 0, but it doesn't matter. I only need one part to be 0. So we'll do the same thing on number 2. What I'd like for you to notice on number 2 that's different is that there's a negative 4 out here in front. You know what? It really doesn't matter. Negative 4 can't be 0, so it doesn't add to anything in terms of giving me new answers, and it doesn't take anything away. The reality is still the same. If either the y plus 3 was equal to 0, or the negative y minus 5 is equal to 0, it zeroes everything out. Yes? What was that, Cooper? I'm highlighting. Can you see the highlighting? That's what I was doing, is highlighting on that one. I just want to be able to refer back to the colors is all. So, all right, so I have my negative 4 here. I'm sorry. I have the negative 4 here. I don't need to worry about it. It's the other two individual pieces that I will set equal to 0 and then solve for. So y plus 3 means I'll subtract my y, and y is negative 3. So that's one solution. On the other one, again, you can do it either direction. I'm going to add the y because then it'll be done immediately. So negative 5 is equal to y. And then that piece is done too. Damaris.
Why aren't they distributing the 94?
Our goal is not to multiply it all out. If that were our goal, we could distribute a negative 4. Our goal is to find where this actually has solutions that make the whole thing equal to 0. So if I distributed the negative 4, it wouldn't change anything. It wouldn't give me any new solutions. It wouldn't take away any solutions. As far as this question is asked, it's irrelevant to the problem. Because if the yellow piece is equal to 0 and I multiply -4 times 0, it becomes 0. So I'm just looking for where each of the individual factors is equal to 0, and -4 is not one of those. Yes?
So our answer would just be y equals -3 and -5.
Exactly. Yeah, so I usually box my answers in. I know I sometimes forget. But yes, those two are two answers to this question. Sometimes we don't have two answers. Sometimes we would just have one. But if that were the case, what would have happened is we would have ended up getting those two boxes that I've boxed in, and they would have just said the same thing. So, okay, as a matter of fact, that's exactly what happens next. So, well, from what Damaris was asking about, that -4. Like, it was weird, right? Like, it was just out there, but it doesn't really affect anything. Sometimes polynomials have a common factor with them, and they can be factored out completely in front, like that -4 was. Sometimes it's a constant, like -4, and sometimes it's a variable. But when factoring, we're going to consider if all the terms maybe have a common factor. Maybe it's a number, maybe it's a variable, and we're going to factor that common factor out in front. So we'll do an example. On number 3, these are not in parentheses form. They're not factored yet. All right, so we're sort of taking these same examples from before, and we're sort of going back a step. It's kind of like number 1 and number 2 are already partially done for us because they're already in this wonderful factored form. And once we get to 3 and 4, that's not the case. They're all distributed and multiplied out, and we have to go backwards to get them into the form that we want. So what I do on number 3 is I look for what 6u squared and -12u have in common. Let's look. Okay, looking at the numbers first, you saw a 6. They're both divisible by 6. And then looking at the variables, what do you see? They both have a u. So I'm going to pull the 6u out in front. Now, pulling that 6u out in front is the equivalent to dividing, right? When I factor it out in front, I'm dividing what's inside by those pieces. So if I looked at 6u squared and I pulled out the 6 and I pulled out a u, or I divided out a 6 and I divided out a u, what will remain? A u. And then on the other piece, you're going a little too fast.
Sorry.
It's okay. The -12u. If I pull out a 6 and I pull out a u, I'm not left with 6, I'm left with 2. And it's negative. Yeah, because you subtracted instead of divided. Yes, Healy.
If you pulled out the 6 and you pulled out the u, in the parentheses, how is there still a u left in there?
Because this says u squared.
Oh.
That's why.
Okay.
Yeah. That u squared means that I had essentially u times u, and I only pulled one of the u's out.
Okay.
So one of them still left. But on the other piece, 12u, I pulled them all out, right? Now, at this point, it's just like the problems from 1 and 2. I have two factors, and I set each one equal to 0. So 6u equals 0, and u minus 2 equals 0. So 6u equals 0, I divide by 6, u is 0. U minus 2, I add my 2, u is equal to 2. Okay, I want to pause real quick. So I found an answer. So I'm going to pick on you just a little bit, Maxwell. I know. So Maxwell originally made a mistake. Give me just a second, Damaris. He originally made a mistake and thought that it was -6, right? So let's say you got to the end of your problem. You would have had two answers. You would have had u equals 0 and u equals 6. How can you make sure that the answers you have are correct? Plug them back into the original equation. So if you'd done that and you got your 6 and you put it back in, you would have realized I made a mistake. 6 didn't work. And then you would know I need to go back and consider what I did wrong. Damaris.
Two things. So first, u equals 2 is the answer, not u equals 0.
Both. I did not. That's what I told you. I usually box them in, and I forgot. There are two answers.
So what I did was I divided both sides by 6u, and then I had u minus 2 equals 0, and I added 2 to both sides and got u equals 2.
Mm-hmm.
But I didn't do that to get another number. Or why do we do that?
Okay, so when you divide by a variable, which is what you did, you lose a solution. And that's exactly what happened when you did that. You lost the solution of 0. I mean, that's what happened, is you can't divide by variables. Now, Damaris, you could have definitely divided by the 6. So dividing by numbers doesn't affect anything in terms of solutions. It's only the dividing by the variables. So we are never going to divide by a variable. We will lose solutions if we try. Okay? Yeah, note to self, right? Don't divide by variables. Interestingly enough, my daughter did that yesterday as well when she was working through her assignment. She tried to divide by a variable. Yeah. And she did it on a problem, I think, kind of like number 4. Number 4 feels like, hey, I'll just divide by y, right? And that seems very natural, but I already told you, note to self, don't divide by variables, okay? So anytime you're dealing with an equation that's not linear, right? It doesn't just have y, it has now y squared. Polynomial equations. We need to have everything on the same side, and we need a factor. So our first step is going to be to move that 19y over with the y squared. So I will have y squared minus 19y equals 0. Okay, now it actually looks a lot like problem 3 that we just did. Right? Everything's on the same side, equals 0's on the right. What do the two terms have in common? Just a y this time, right? And if I take a y out, what will I be left with? Fabulous. Y minus 19. Now it looks like a problem from 1 and 2. I'll set each piece equal to 0. The first one's already solved. On the second one, I'll add my 19. And y is equal to 19. So 2. Y is equal to 0, and y is equal to 19. 2 solutions. Yes, Gayla.
Okay, so you said like on number 2, the 4 doesn't pull out
Yep.
and equal to 0. So why does, on these problems, why does it equal to 0?
Okay, so the difference is that 4 is a number and y is a variable. So, for example, on this one, when Damaris was asking me about dividing things, you actually could divide by the 6. It'd be okay. So if you wanted to divide everything by 6 and end up with u squared minus 2u and then factor that, that's okay too. Yeah. So you can divide by numbers. You can't divide by variables. In fact, if you want to think about that dividing by numbers bit and you come back over here to problem number 2, we also could have done the same thing here. We could have just divided both sides by -4 to start with and just removed that from the, the consideration entirely. And that would have been fine. Remember, dividing by -4 would cancel the -4 out on the left, and then 0 divided by -4 would be 0 on the right. So numbers we can divide by, variables we can't. All right, so I keep using this word polynomial, and I think it'd probably be a good idea to sort of define it more specifically. So a polynomial in general has the form that you see below, right? It says a sub n x to the n, a sub n minus 1 x to the n minus 1, all the way down to a sub 2 x to the n, a sub 1 x plus a 0. Okay, so slow down for me for just a second. Here's what you need to know. All these little a subscript things, those are just numbers. Okay? I'm going to call them a sub I are numbers. And that letter n, or the n, are not integers, whole numbers. So I'd like to give you some examples and some non-examples because I think that's actually a little bit easier to look at than the general description that's at the bottom there. So we can have fractions like 1/2 x squared plus 2. Okay, we can have fractions. That's cool. We can't have fractional exponents like x to the 1/2. That's a no-no. We can have whole numbers too, like 3x cubed minus 7. We can even just have 3x cubed. Okay? But we can't have negative exponents. So we couldn't have 3x to the negative 3 minus 7. Our last section of material, we did linear equations, like y equal 4x. 4x is actually a polynomial as well. It's a more general description. Do you guys remember from geometry when you would define things like this shape and it would have lots of names? The most specific name, if I'd drawn it really well, would be square, right? But it's also actually a rectangle and it's a quadrilateral. It's got lots of names, okay? It's kind of like that. 4x very specifically, like y equal 4x would be a linear equation, but it's also a polynomial equation more generally speaking because it fits the description below. You can have single terms like this, 4x. You could also have things that were all added together like we had in the previous examples, but here's another one. So it could have 3 terms, it could have 4 terms, it could have 5 terms. The important thing is that the exponents are positive whole numbers. You also can't have things like a square root. That's not one. No square roots. Square roots are not polynomials. And you all said...
Yay!
Thank you, Maxwell. Yes, I know you aren't fans of square roots. They won't show up. We're not dealing with them in this section.
Finally.
You also won't have to deal with any variables in the denominator. We haven't done anything with those yet, but eventually we will.
No.
We will. Just not today. That's not a polynomial. So polynomials tend to be very friendly equations. They're not as friendly maybe as the very specific type of polynomial that's linear equations, like in the last section, but they're fairly friendly. Now there are a couple of types, or one type specifically of polynomials that it's worth mentioning because we do a lot with them. That's quadratic. A quadratic is a specific type of polynomial of the form, and this is the one you're most used to seeing, ax squared plus bx plus c, right? Y'all remember that from the quadratic equation? Yeah, I'm not asking you to do the quadratic equation right now, but that's where you see it, probably that's in your memory. We call the leading coefficient the coefficient of the largest degreed term. So it doesn't really matter whether it's at the beginning or not. It's just wherever your x squared or x cubed or x to the fourth, whatever your biggest exponent term is, the coefficient on that is called the leading coefficient. And the leading coefficient, along with the power on the exponent, determines a lot about what the equation will do. How fast it's going to do things, whether they're going to be positives or negatives, because it's going to dominate everything else, because it's the biggest degreed term, and it's the coefficient of that term. So I've used a couple other of these words today. I think maybe even all 3 of them. Monomial is a single term expression. For example, 4x, I did that before. A binomial is a 2-termed expression. For example, if you had x plus 7, so terms are separated with addition or subtraction. That's what makes it 2 separate terms here. Whereas 4 and x are connected with multiplication, so it's a single term. Okay? And a trinomial is a 3-termed expression. And maybe that looks like x to the 4th plus 2x minus 6. Okay, so it doesn't necessarily have to be a quadratic trinomial, but it could be something else. Yes, Bailey?
Why is that one a try and the one before?
Because I have 3 terms separated with addition and subtraction, and this one only has 2 pieces separated with addition and
the
subtraction.
quadratic one, sorry.
The quadratic one is a trinomial. It is. It's just a very specific type of trinomial that has a power of 2 only. Okay? So it's kind of like classifying me as I'm a mom, and I'm a teacher, and I'm a wife, and I'm a pastor's wife, and I have lots of titles, right? But it's still all talking about the person me. So what you're seeing up here where it says ax squared plus bx plus c is a quadratic equation. More specifically, it's a quadratic polynomial, or it's a quadratic trinomial, because there's 3 terms. Kind of like when you do triangles too, right? We can classify them by the side lengths, or we can classify them by the angle measures, or by how they're related to one another. It's like that. So the polynomial at the top, that quadratic, is a trinomial, but specifically it's quadratic. The one that I listed on the bottom here is also a trinomial, but it's not quadratic because it has a power 4.
Okay.
Okay? All right, we are going to solve some quadratic polynomials specifically. I'm going to show you a method that you may not have seen before. Okay? It's called the AC method. And then we're going to do it with trial and error, which is probably my favorite because that's what I learned first. And it may be what you learned first as well. Trial and error is really nice if you happen to try something that works pretty quickly. Trial and error becomes far less nice when you try things that don't work. Are you with me? All right, the more things you have to try, the more frustrated you typically become with trial and error. So I want to show you a method that sort of always works. It's got more steps, so I'm going to warn you on that. But it always works when trial and error sometimes leaves you feeling like, I've tried everything. Probably haven't, but I've tried everything and it didn't work. So I'm going to show you our AC method first. Okay, so over here we had a quadratic equation, the one that Bailey was asking about, that was ax squared plus bx plus c, right? So a is the number being multiplied by x squared, b is the number multiplied by x, and c is the constant. Okay, just for a reference point. So the first thing we're going to do is that we're going to multiply a times c. So what is the a term in this polynomial?
U squared.
Okay, it's the coefficient in front of u squared, which is the number
U.
1.
No.
Number, yeah, 1. Times, and what's c in this problem? 10. So AC here is 10. Agreed? Awesome. B, we don't have to multiply anything. What's the B value for this one? -7. Okay, is everybody good so far? So you're identifying what is A times C and what is B. And you ask yourself this question. I'll write it at the bottom of my screen because we're going to ask ourselves the same thing later. What two numbers, I'm shorthanding things, that's not a hashtag. What two numbers multiply to A times C, so in our case 10, and add to B? That's the question that we're being asked every single time. I'm going to make that even a little bit bigger because I have some space now to do so. Whoops.
-5 and -2.
Okay, so what did you say?
-5 and -2.
-5 and -2. Those two numbers multiply to 10, right? Yes. And they add to -7, right? Yes. So here's what we do. We take this term here in the middle and we rewrite it using those values. So here's what I'm saying. Here's u squared. And I'm going to have -5u and -2u. And I'm going to have my positive 10 equals 0. All I'm doing is I'm breaking -7u apart, very specifically into -5u and -2u. Okay, I know you don't necessarily see where this is heading just yet, but do you agree that that's equal to the previous step? That's all I'm asking for right now. It's equal to what we had before. Okay? All right. What we're going to do next is we're going to group the 2 at the beginning together and group the 2 at the end together. Starting with the 2 at the beginning. U squared minus 5u. What do they have in common? U. If I take a u out, what am I left with? Fabulous. That's factoring like we've done on the previous problems. Now, on the second one, my goal is that what's in parentheses matches what was in parentheses on the other one that I had. If it doesn't, then we have a problem and we've made a mistake somewhere. The parts in parentheses must match. So, I not only have to bring out a 2 for them to match, I have to bring out a -2 for them to match. Is everybody with me on the negative part? Because that's the tricky part, I think, to sometimes see. So when I pull out a negative 2, I'm left with u. And if I pull out a negative 2 from a positive 10, I'm left with, again, the minus 5 that I was looking for. Okay, so again, may not see where we're going, but do you agree that that's equal to the previous step?
Yep.
Fabulous. Now, I'm going to do a little bit of highlighting. I want to highlight everything in the first part, and I want to highlight everything from the second part. So I've got a yellow piece and I've got an orange piece. What do they have in common? The u minus 5. Okay, is everybody with me on that?
Yep.
So we are going to factor the u minus 5 out in front, and we will be left with u and minus 2. This piece is left, and this piece is left.
So when I was taught it, I don't even.
Because you're using trial and error. We're doing it next, I promise, Maxwell.
Okay.
I promise. This question is not a hard trial and error question. It isn't. I know that. But I want to show you that even on one that's easy with trial and error, for those of you who feel like I could do this without having to do all that work, and I get it, it will still work.
Oh, I was still talking about the AC method. It's just.
Oh,
Once
I'm sorry.
I found the like -5 and -2, my teacher, all she taught me is you can just do u minus 5 and u minus 2.
And that works as long as your coefficient on u squared
Yes,
is 1,
As long as it's 1. If
which
it's
it
not
won't
1,
be in
then
the
you have
next
to slide
lesson.
and divide is what she said.
Yeah, I don't do slide and divide because it makes things mysterious. So we're not going to slide and divide things. If you love slide and divide, I'm not saying you can't use it, I'm just not teaching it. Okay? All right. From this point, y'all know what to do now, right?
Yeah.
What are we going to do? Yeah, each part equal to 0. U minus 5 equals 0. U minus 2 equals 0. And if I add my 5, u is equal to 5. I add my 2, u is equal to 2. And how could I check to make sure it really is the solution? Plug it into the very original equation I first started with. Okay, so I am not asking that you have to do this particular method, but I want to show it to you one more time, okay, so you can see it play. And then when you get to your homework, you can decide what you want to do your own. All right, so A times C. 1 times 25. And in this lesson, it's always going to be 1 times something. When you get to the next lesson, 2, 3, which is our continuation of polynomials, it's not always going to be 1 times something. It's going to be other numbers. So 1 times 25 is 25. And then what's B? 10. So I need two numbers that multiply to 25 and add to 10. Yeah, 5 and 5. Okay, so my two numbers are 5 and 5. Right, these are my magic numbers. So I will rewrite the W in the middle as plus 5W. I'm sorry, the 10W in the middle as plus 5W plus 5W. I've got my plus 25, and it equals 0. Okay, the original part, all I've done is I've broken the 10 down into 5 plus 5. So this piece became these two pieces. That's what you should see happening. That's the AC method at work. Okay, so now I'm going to take the pieces one at a time. 2 at the beginning, 2 at the end. Oh, let me make one more mention too. On the first one, I chose to do minus 5u first and minus 2u second. Did y'all saw that? There's absolutely nothing about that that's special. If I had done minus 2u first and minus 5u second, it still would have worked. Okay, so I just want you to know that that's actually something that's really nice about the AC method is that the order won't end up mattering when you're working through it. All right, w squared and 5w, what do they have in common? A w. So I take out a w and I'm left with what? W plus 5. How about 5w and 25? 5. And if I take out a 5, I'm left with? W plus 5. As long as it's all addition, I don't even have to worry about negatives, which is very friendly. Of course, these w plus 5s, they match. So I factor it out in front. And on this one, I'm left with another w plus 5 equals 0. I can set each part equal to 0. They happen to look exactly the same this time. I mentioned that being a possibility earlier. We hadn't seen one yet. So on this one, w equals -5 is the only solution. It happens twice. You don't necessarily have to write it negative, or the w equals -5 twice, because there is only one solution to that particular problem. Okay, let me run through trial and error real quick. Trial and error works really nicely when you have a coefficient of 1 at the beginning. It really does. So the way that trial and error works is that you flat out start with the parentheses, and you ask yourself questions something like this. What times what equals u squared? U and u, right? I don't have any choices here. Signs. Well, the sign here at the end being positive means my signs have to match, right? And they'll both be negative because the middle sign's negative. So I'm going to have a negative and a negative. I feel like there's more pieces to remember as you work your way along with this, like that sign business, if you do trial and error, but that's okay. And now I need two numbers that multiply to 10 and add to 7. 2 and 5. And of course, you're back to the same place we were before. U is 2. And U is 5. Okay, pros and cons. Pro, it's a lot faster. No question. Con is that it works really nicely, but only sometimes does it work really nicely. 10 was a nice number. There really weren't a lot of options that you had to think about because 10 doesn't have a lot of factors. If you had the number 36 at the end there, you got a lot more factors of 36, right? So it takes a little bit longer processing through all of my factors, and depending on how good you are at factoring as well. So let's try 8. So I need two values that multiply to w squared, w and w. All the signs are positive here, which means so will these be. That's friendly. And then finally, I need two numbers that multiply to 25 and add to 10. 5 and 5. Again, very nice, because there really aren't a lot of factors at 25. And then if I set each one equal to 0, I get w equals -5. So, I don't care which method you use. Yes, ma'am.
I'm trying to figure out something. I was gonna say this is the same thing as the two we did before.
Is it the same what?
Like, it's the same thing, it's just two different things.
Yes, exactly. These are the exact two same problems in two different methods, and you can pick what you like. All right. We're going to rewind. This is our last thing for today. We're going to reverse this process. We're going to be given the solution of a polynomial equation and asked to find the equation that it matches. Okay, this is actually very friendly. This one tells you the roots. Roots means solutions are 6 and -3, and it has a leading coefficient of 4. Okay, those are the important pieces. So what that means is that you're going to set up the equation that goes x, and it will subtract each of the roots. So x minus 6 and x minus a -3 equals 0. Where it says the leading coefficient is 4, it means you put a 4 in front.
So we're not using the quadratic equation?
Nope, we're not quadratic equationing. We'll get there eventually, but that's not what we're doing today. I'm so sorry. All right, so as we do this, I have 4, I have x minus 6, and I have x plus 3. And I will FOIL or distribute this out. So I'm in a FOIL, which means I'll do first, which is x squared. I'm totally going to run out of space, so I'll move things in a minute. So ignore this question for the moment. We'll do it on the next slide. So here's 4 times x squared. Inner terms is -6, and the outer terms, inner and outer. So the inner is -6, the outer is 3x. So -6 and +3 is, actually, let me just write it out. -6x, +3x. Inner terms, outer terms. And then my last terms are -6 times 3, which is -18. X squared minus 3x minus 18 and then we're going to distribute the 4 through. I suggest distributing the constant through at the very end. It keeps the number smaller longer. So 4x squared minus 12x, minus, what's 4 times 18? I have 72. Do you see why this is the reverse of what we did before?
So you have to FOIL before you distribute.
You don't have to, but I do, because the numbers will stay smaller. I'm a fan of smaller numbers as long as possible. Yeah. Okay, let's do the last one real quick. It's not on this slide, but it says the roots are 5 and 2, and the leading coefficient is 2. So leading coefficient being 2 means there's a 2 at the beginning. The roots being 5 and 2. The root being 5 means I've got an x minus 5. And you could use another letter. It doesn't have to be
Is
x.
it always minus?
Yeah,
Yes. It's always minus this value. And the reason that happens, let me just show you real quick from when you did it before, is do you notice u minus 2 corresponds to u equals 2? It moves.
Oh.
Remember that? U minus 5 corresponds to u equals 5. W plus 5 corresponds to w equals negative 5. It's always the opposite sign. Yeah. And this is set equal to 0. Please remember set equal to 0, otherwise it's not an equation. Okay? So first is x times x, which is x squared. Outer is x times negative 2 for negative 2x. Inner, negative 5 times x, which is negative 5x. And last is negative 5 times negative 5, which is positive 10. Okay, you'll recognize that we've seen this before today. X squared minus 7x plus 10. We did it twice, right? The other direction. We didn't have a leading coefficient of 2 last time, though, so we'll distribute our 2 through, and I'll have 2x squared minus 14x plus 20 equals 0.
Now, if we wanted to, could we use a quadratic equation?
To solve it, but that's not what the question asked you to do. The question asked you to create any quadratic equation. You're thinking about the quadratic formula when you hear the phrase quadratic equation.
Oh, I love
All right, so this lesson is due on Monday at 9 a.m., just like always. I'll post a separate video that's got section 2.3. That will be due on Tuesday when we get to class. Okay, we'll do questions and so forth from that. Questions from 2.2 that we just did, you should direct them to me via email, or you should go to the Success Center on Sunday night. Those are your choices on that. Or you can talk with one another, of course. Have a great weekend, guys.